growing demand of NVM in all the products. In the figure here we can see that application of NVM is varying from industry and transportation to enterprise storage, MCU smart card and other markets, wearables, mobile application and mass storage memory. These NVM require high positive and negative voltage to perform memory write erase operation. These high voltage are generated on chip using charge pump and regulated through voltage regulators. In this slide, we will go through the problem statement. So we require different negative voltage for different operation of flash memory. For erase operation, we require a very big negative voltage, and for program and read operation, we require a small value of negative voltage to reduce the leakage of non-selected sector. So these different configuration of negative voltage should be linear and accurate. Also, ripple of outputs should be very low to improve efficiency of all these different operations. In this slide, we will go through the previous work which has been done. In the A figure, here we can, in this architecture, VNAG is generated with the help of negative charge pump directly, and VNAG is regulated with the help of comparator and oscillator. So when we will reach to desired VNAG value, oscillator will be cut off and CK1 and CK2 will be off. The advantage of this architecture is it is very simple, but main disadvantage of this architecture is that the ripple at VNAG will be very high because it is coming directly from negative charge pump. To reduce the ripple at VNAG, we require a very high value of load capacitance, which will result in higher area. In the next architecture, to reduce the ripple at the output voltage, they have used one regulator and used a negative charge pump as the supply of this error amplifier. So here VNAG will be generated such that it will be 1 plus R2 upon R1 into Vref minus R2 by R1 into VDD. To achieve the different configurability of VNAG, they have configured the R1 with the different switches. If we use large configuration range with multiple output levels, then many switches are added in series to make R1 configurable. These series switches implemented with transistor will operate in body effect, and switch resistance will be significant enough to be considered. This will cause an error into the negative voltage required. Also, here we can see that VNAG is directly dependent on VDD. To any switching noise introduced on supply due to large current requirements and finite supply resistance will also impact the VNAG value. To cater these problems, we are proposing a architecture which is made based on a DAC and the error amplifier. Here we see that VNAG will be V ground minus R2 into IDAC, and we are using reference as V ground voltage, so VNAG will be direct minus IDAC into R2, and this IDAC is different value of IREF, like VNAG will be minus N into IREF into R2, and here N represents the decimal equivalent. It will be 32 for 000 and 0 for 111. And this VP gate and V is the mirroring voltage which is used to generate IREF current, and cascade voltage is used in the current mirror architecture to improve the efficiency of this current mirror. In the next slide, we will discuss the biasing generation of VP gate and VCAS. So IREF is generated such that it will be a ratio of Vref upon R1, and Here in the previous slide, we can see that Vnag is minus n into Iref into R2 and Iref is Vref upon R1. So Vnag will be the ratio of minus n into Vref into R2 by R1. If R1 and R2 are well matched, then we can reduce the variation of temperature and process at the Vnag value due to resistance. And the cascade voltage required is generated such that it will be summation of Vp gate plus VGSP13. So it will adapt across the process voltage and temperature with the help of VGSP13, and our current mirror will work in the required with the required voltage and required configuration. In this slide, we will discuss the negative charge pump architecture. We are using a negative charge pump architecture which is made of only the NMOS, because we cannot use the PMOS based architecture, as our ground or substrate will be at ground, and any N based terminal which is lesser than ground will create in the static current path. And to improve the efficiency of this charge pump, we have used the gate boosting method. So this architecture of negative charge pump requires 4 different clocks. So here we can see the different clocks required, and P denotes the pumping clock, and here B denotes for the boosting clock. We have used 7 stages for negative voltage generator, employing only the NMOS as transfer switched. And the CB denotes the bootstrap capacitor, and CP and CPL denotes the pump capacitor and load capacitance respectively. Vnag CP output of negative charge pump can be given as Vnag CP 0 plus I load into RCP. Here Vnag CP0 is minus n gamma Vs. So n is the number of stages and gamma Vs shows the gain of each stage, and RCP is the output impedance shown from the negative charge pump. This output impedance will include 2 terms. One is the impedance shown by the switches, and this is the impedance shown by the capacitance, and it will be multiplied by the number of stages. In this slide, we will discuss the transistor level implementation of the error amplifier which we have used, and we have stacked the different different biasing voltage to reduce to make all the transistor work in the safe operating area, and we are stabilizing this circuit with the help of ESR and a very high value of CL of 10 picofarad. In these slides, we will discuss the results. In the first figure, we can see the different DC value of Vnag CP across varying current load with different frequency. For 30 megahertz, the DC value of Vnag is changing from minus 11.3 to minus 10.5, but for 40 megahertz and 50 megahertz, the value of Vnag CP is very stable, as the output impedance of NAG CP will be very low, so effect of current load will be also very low. But in the second picture, we can see that for how the efficiency of our negative charge pump will change for different frequency. Here we can see in the blue curve for 30 megahertz we will have a higher efficiency for lesser currents, and for higher frequency we will have a good accuracy but for the higher current load. And this accurate efficiency of charge pump is given by Vnag CP into I load upon the total current consumption from the supply. So in this slide, we will see the transient response of our circuit. So this is the VNAG value for zero DAC current. It is around minus 0.23, and as we are changing the value of current to to 32 microampere, our VNAG is also changing to minus 10.36 voltage, and the value of VP gate and VCASC is almost stable for different DAC current. In this curve, we will are showing how our regulator is improving the ripple voltage. In the charge pump is giving us a ripple of 171.66 millivolt for peak to peak, and output of VNAG is only 3.5 millivolt for a current load of 31 microampere. In this slide, we will see the AC response of our error amplifier for two volt extremities voltage for 0 volt and minus 10 volt. The 0 volt results are shown with the green one, and blue curves are for the minus 10 volt. Here we can see for 0 negative voltage we have worst case phase margin of 59 degree, which is 83 degree for minus 10 volt. And in this curve we are seeing why our ripple on the VNAG is very low. As here we can see the negative power supply rejection ratio for voltage regulator is minus 68 dB for 30 megahertz. So it is suppressing all the noise on VNAG CP to VNAG. In the summary table, we have used the 90 nanometer triple well technology, and our supply is varying in 3.3 volt and 1.2 volt. 3.3 volt is used for charge pump circuit, and 1.2 volt is used as the supply of the regulator. We have a VNAG range of 0 volt to minus 10 volt, and maximum load current for our circuit can be up to 200 microamperes. So we have a load regulation of 95 microampere upon microvolt. Ripple at our output is around 3.5 millivolt with the highest current load, and power consumption from our circuit is 8.86 millivolt at 30 megahertz, and total area consumed by our circuit is 0.11 millimeter square. In the next slide, we will see the conclusion. The voltage regulator with current-based digital to analog converter is used to regulate the output of negative charge pump. The current DAC is implemented in cascade configuration to increase its output impedance and reduce the impact of supply variation. The PLA simulation results validate the effectiveness of proposed solution. Thank you, everyone.
Okay. So looks like there is no questions on this, but let me ask one question, Vivek. I think you presented. So the idea.
You can, Mr. Punara.
Yep.
There are no questions, but you can ask some questions if you have any with the speaker.
Yeah, I will. I have one question. So that IDAC settings is need to be trained or trimmed across the process, Vivek, or it's one-time setting is good enough for across process?
I assume yes, side. So we have this IDAC is the combination of IREF, like for it is N into IREF, and it was across process we have trimmed with the help of R2. So we have seen in that IREF will be the VREF by R. So across process we have to trim the value of resistance to have a stabilized IREF.
Okay, the trimming is needed. And second question is, do you have a relative comparison of power with respect to the state of art previous works? It's relatively is better in terms of overall power for the same load current, or it's how is the trend? Because you introduced IDAC. Yeah.
Yeah. So we have there are two state of art, and from in one the power was less, and in other it was working at 50 megahertz. So total power number was higher than our, because we are working at 30 megahertz. So there was two state of art reference, but we haven't compared at the 30 megahertz the second one. But for first one, surely it was lesser than our power numbers.
I see. Okay. Thank you.
Hello, this is Vikas from ST. Just to add, actually, more than power, we have a much better control on the output voltage. So
that I completely agree. Yeah.
Because specifically for the non-volatile memories like flash, we need to have a very precise control on the output voltage in terms of the slope, in terms of the ramp, and that is very precise with this kind of architecture.
Yeah.
And that is the main specification targeted, let's say.
Yeah, makes sense. Yeah, that I agree. Yeah. So I think thank you, Shivam, Kalla, Vikas Rana, and Vivek Tyagi. And we are going to the next one. It is very interesting. High voltage receiver using low voltage devices with reduced dead zone. I'm just trying to. It is going to be presented by Dharmarai Nedalgi from Intel and Saroja Siddhamal and KLE Technological University. I'm going to remind one more time, please. Any questions in the presentation, please feel free to enter into the post. We'll definitely ask those questions. Yeah, please admin, start the second video.
Hello to everyone watching the presentation. My name is Dharmarai Nedalgi. I work with Intel Technologies India Private Limited in Bangalore. In this presentation, we cover high voltage receiver using low voltage devices with a reduced dead zone. In the content, we cover first the problem statement, then the standard existing high voltage receiver, then we go over the proposed design change and the simulation results and conclude the presentation. The problem that we are defining here is to design a 1.8 volts receiver using 1 volt devices. All the design and the simulations are done using 22 nanometer FinFET process. Most widely used high voltage receiver is what you see in the diagram, with the stacked transistors, 2 protection devices N2 and P2 with the gate connected to VDD, and 2 receiving devices N1 and P1 who receive the input signal, which was split into 2 parts. Input signal splitting into 2 parts, to one going to the N side and another going to the P side. When input signal is rising from 0, pass transistor N3 conducts and Vin is connected to Vin NS. And Vin NS follows the Vin as long as input signal is VDD minus VT. At VDD minus VT, the pass transistor N3 cuts off and Vin NS remains stable. And Vin can continue to increase, and Vin PS doesn't change until the input voltage crosses VDD plus VT, because till then pass transistor P3 is off. And once Vin crosses VDD plus VT, Vin is connected to Vin PS and Vin PS follows the input beyond VDD plus VT. In between VDD minus VT to VDD plus VT, both these signal nodes Vin NS and Vin PS remains constant. and receiving devices N1 and P1 are not sensing any change in the input signal. This range of signal between VDD minus VT to VDD plus VT, where the receiver is not sensing any signal change, is what we call as a dead zone. Receiver is basically dead at that point in time and it's not sensing anything. And receiver starts responding only when the input signal crosses beyond V1 or V2 depending on the direction of the signal. This adds the delay to the receiver. Apart from that, when input voltage is at VDD to VDD level, the Vin NS is at Vin minus VT and N3 is off, and this Vin NS node becomes a high impedance. Similarly, Vin PS when input is at 0. These high impedance nodes are susceptible to any coupling in a noisy environment. And any noise can couple in the range of 280. Beyond 280, two diode connected devices N4 and P4 bring them down as a protection. And this uncertain coupling at the two receiving nodes Vin NS, Vin PS can lead to change of switching threshold of this receiver, which lead to a jitter into the received signal. Apart from that, and this additional voltage that can come anything higher than VDD at a Vin NS can cause over voltage stress to the device N1. Similarly, Vin PS will cause the stress on the P1 device. In the proposed design, we are proposing to change the previously diode connected transistor N4 and P4, and their gates are connected directly to the input signal instead of Vin NP and Vin PP. In this case, when input voltage exceeds 1 VT higher than VDD minus VT, that is at VDD level, anything input crossing more than VDD, N4 starts conducting, and which will take the Vin NP higher and goes up to VDD. Similarly, when it is falling side, if Vin falls anywhere beyond VDD, it starts P4 starts conducting and brings the Vin PP to VDD. These N4 and P4 switch between diode connected configuration and the switch transistors, depending on the level of the input voltage. When input voltage is between 0 to VDD minus VT, N4 is diode because its gate is connected to Vin through N3 and its source is connected to Vin NP, which is again connected to Vin through N3. Similarly, for other range to Vin PP. When input voltage is either of the 0 or 2 VDD, both the node Vin NP and Vin PP are well defined to 0 or VDD, or VDD and VDD, or 2 times VDD, depending on the state of it. When input voltage is at 0, Vin NP is at 0, Vin PP is at VDD. When input is at 2 VDD, Vin PP is at 2 VDD and Vin NP is at VDD. All nodes are well defined and this removes any possibility of coupling so that there is no additional jitter added into the final receiver output. This also reduces the delay in the signal, as the receiver starts responding at T3 instead of waiting till T2. If you see the simulation results in the first part, in a noisy environment, both the designs are exposed to the exact same noise scenarios. The proposed high voltage design performs far better because its intermediate signals are well defined here, whereas in the previously standard used receiver, the intermediate signals are noisy and they are having some coupling depending on the amount of switching in this environment. And this gives us the very clear eye diagram, and in the proposed high voltage receiver you see absolutely no jitter, whereas in the standard we have an amount of jitter available in the magnetic receive signal. On the right hand side you can see also a transient response, complete both the design responses are overlapped with each other. Dotted response is what is the existing high voltage design, and the solid lines represents the proposed high voltage design. You see the solid lines are well defined, whereas in case of dotted lines, the two intermediate nodes are at high impedance, and because of that there is variations in them. And proposed design is much more faster than the existing design because of the reduced dead zone by 1 BTU. In the finally concluding, what we say is proposed high voltage receiver reduces the dead zone compared to the standard high voltage receiver design in the literature, and proposed design does not add any extra device. It has exactly same area as the previous design. Just what we do is a change of the gate connections. And this design has a better performance in terms of speed, duty cycle distortion comparison with the standard design. With that, I conclude with some references for your detailed references if you want to go through. So there is anything. Thank you, and let me know if you have.
Thank you, Dharmarai. Just still same. So one question, that this one doesn't give any, doesn't impact any UAs, right? I think it is similar to the previous.
Exactly. So we are not covering the US part of it. So it is identical to what the previous design is. There is no change in that part of it. Yeah, yes, there are issues for both the designs that we need to address separately. In this paper, we didn't address that part of it.
Okay. Thank you. Okay, so then let's start the third.
Sorry.
Yeah. So sorry. Go ahead. Yeah.
Can I go ahead and ask a question, please?
Please, sure.
Go ahead, sir.
Please
go ahead.
Thank you. So, next presentation, I just wanted to know what are the typical headroom which you have?
Headroom in the context, maybe if you would make it little more clarity for me, because
yes. So,
in this presentation it is more of a supply is of 2 voltage levels, 2 times the device capability. That's what we are looking at. Maybe if we could explain a little more, I can answer to that, please.
No, exactly. Well, that's what we mean to say also, that if you have a voltage supply VDD and the overdrives, if you add between VSS and VDD and you subtract from VDD, that is effectively the voltage room available to us. So I just wanted to know typically how much overdrive is there for this design.
This design has hardly any overhead here, dead room, because the device is capable of 1 volt. The actual supply is already 1.8. So rather than in the simulations, you see that we have actually taken it, I rather didn't give an exact value. It is device level
you can go 2 times the supply capability of the device. So if if your device is 1 volt capable, you can go to 2 volts. If your device is 2 volts capable, you can go to 4 volts, or it's a lower side. So depending on this design is meant to use in a higher voltage than the device capabilities.
Correct. Thanks a lot. Thank you very much.
Thank you.
Thank you, Dharmrai.
Sorry, I have one question. This is Vikas.
Sure.
Go ahead, please.
How the bulk of PMOS and NMOS transistors are managed? Are they made in conventional CMOS technologies, or you need some triple well technology for it?
No, NMOS devices in this particular case is used normal, not a triple well. PMOSs, all of them are connected to 2 VDD, so that is also visible. But PMOS is possible within the same technology, but we didn't do that variations because the well was able to handle up to 2 VDD. That's why we didn't manipulate that part of it.
Okay, yeah, because if the output of this circuit is 2 VDD, let's say the PMOS path is enabled, then NMOS drain to bulk junction will be in stress if you bias the bulk of the NMOS to ground, right?
Yes, bulk to drain is still much more capable handling the device than the gate source or drain source, or even gate to drain. Its bulk is more robust than the other 3 terminals in general technology.
Okay, yeah, thank you.
Thanks. Let's move on to third one. This is very state of the any chip you need to have minimum ring oscillator. We are going to present by the team of the KLE Technological University. Ring oscillator with improved design. I'm just go the first names only. Sorry because of time saving. Pooja, Priyanka, Prudvi, Suma, Sujata, and Shraddha. So these are all the team is going to present the ring oscillator. Let's start the third one.
Hi everyone, I'm Pooja Shanbhag from KLE Technological University, Hubballi, Karnataka. Today I'll be presenting you the ring oscillator with improved design. This is the flow of the presentation. First we'll look into the design specifications, architecture, its individual blocks, and simulation results. Later we'll wind it up with conclusion and references. Before we move to the architecture, let's get back to the basics. What is a ring oscillator? A ring oscillator is a series of inverters connected in a closed loop. Typically, odd number of inverters. With even number of inverters, we'll end up building a latch. These inverters are used as delay cells. Mathematically, a system to oscillate should meet Barkhausen criteria. Barkhausen criteria says that the loop gain, that is the magnitude of A beta, should be equal to 1 and the phase of the loop should be equal to 0 degrees or 360 degrees. That is, the feedback signal should give 180 degrees of phase shift. The oscillation frequency is given by a formula 1 divided by n into propagational delay, where n is the number of inverters. Here in the image, n is 3. Oscillators generates periodic signals and its use can be found in applications like PLL, wafer testing, clock generator, microprocessors, IoT applications, and many more. We had to design and implement a ring oscillator that meets the following specifications. We had to meet the frequency of 1 megahertz and 50% of duty cycle at 1.8 volt supply voltage with plus or minus 10% variation in supply for a temperature range of minus 40 degrees Celsius to 125 degrees Celsius. This is the block diagram of the architecture. The whole architecture is divided into 4 blocks. They are voltage biasing circuit, starting with the chain, followed by a multiplexer and an output buffer. In the further slides, we'll be looking into the details of individual blocks. This is the the first block of the proposed architecture, that is voltage biasing circuit. This is required to compensate the temperature variations of the stacked inverter chain. It was observed that the stacked inverter chain showed CTAT behavior, that is complementary to absolute temperature. In order to compensate that, we need a PTAT generator, that is proportional to absolute temperature. So we used a PTAT circuit as voltage biasing circuit. Here is the image of the PTAT circuit. The next block is the stacked inverter chain. Here is the single delay element of the stacked inverter. This is the core block of the architecture. Each delay element comprises of 3 inverters. This improves the delay in each stage and also enhances the gain, as there are 3 inverters here. Odd number of stacked inverters are cascaded to work as an oscillator. Here, the output voltage swing depends on the charging and discharging current. In order to achieve a frequency of 1 MHz, 11 such stages were required at typical case. Here, Vy is the input of the inverters and Vin is the supply voltage. In the first cycle, M1, M3 and M5 will be turned on, that is when the input is low, and when the input is high, M2, M4, M6 will turn on and rest will be turned off. This is the stacked inverter chain. Here we can see that the output of the first stage goes to the input of the gates of the second stage. That is, VL is connected to the gates of the second stage. The last stage output is fed back to the first stage input. It was observed that the delay across different corners was different. So in order to achieve the same frequency across all the process corners, multiplexer was used. Multiplexer, which is also known as mux, is a data selector which has multiple input lines and it feed forwards a single output based on the select lines. Here, multiple feedback lines is fed to the input of the mux. These multiple feedback lines come from the output of different stages of stacked inverter. The delay across different process corners was noted down and the stages were decided accordingly. The select lines are used here as trim bits, that is T1 and T0. Apart from T0 and T1, there is one more bit which is controlling the MOSFET in between the stages. This MOSFET acts as a switch. This is added because in order to eliminate the delay of the other stages when they are not in a closed loop at a particular process corner. Here, Vx, Vz, Vw, Vy shows the different multi-feedback lines of the stacked inverter chain at different process corners. The next and the last block of the architecture is an output buffer. A buffer you use to get a square wave and a rail-to-rail output swing. The output of the multiplexer is input of the buffer and also the input of the stacked inverter. Duty cycle is also adjusted by sizing the MOSFETs of this buffer. This is just two inverters connected in series which acts as a buffer. Here is the final schematic of the proposed architecture. This is the voltage biasing circuit. The supply to the stacked inverter chain is the output of the PTAT circuit, and here the multi-feedback lines are fed to the mux across different corners, and it is controlled by the trim bits T0, T1 and T2. From the mux, the input is fed to the buffer, which is the output of the multiplexer, which also goes as the input of the stacked inverter chain. We can see the oscillator output at this point, that is the output of the buffer. This design has been realized in GPTK 90 nanometer technology using Cadence Virtuoso schematic editor. Here's the output waveform of the oscillator at typical corner. We see that it's a clear square wave, rail-to-rail output swing of 0 to 1.8 volts. We observed a 47% of duty cycle in this case. The calculation are shown here. The T on was equal to 0.49082 microseconds and total time was 1.0375 microseconds. Hence the duty cycle turned to be 47.2%. This is the output waveform across different corners. The trim bits which are decided to control the stages across different corners are shown in the table here. The frequency variation across different process corners are also noted below. All the variation was within 5% at 1.8 volt supply and a temperature of 25 degrees Celsius. Here's the results of frequency variations with respect to temperature at 1.8 volt supply. Initial frequency variations with respect to temperature was very huge. It was from 3.75 Mach to 0.72 Mach. In percentage, it is plus 191% to minus 34%. After using PTAT circuit for biasing, we achieved the frequency variation with respect to temperature around plus 11% to minus 14.4%. It was reduced significantly. This is a frequency variation with respect to supply voltage at 25 degrees Celsius. It was found around plus 12% to minus 14.7%. Here's the frequency variation with respect to supply voltage across different process corners at 25 degrees Celsius. The frequency variations with respect to temperature across different process corners at 1.8 volt supply is shown here. The variations are noted down in the table. This is the trim bits used across different process corners and variations are found as follows. Across TT corner it was minus 14.4 to 10.9%. At SS corner it was minus 11.2% to minus 3.1%. At SF it is minus 10.1 to 8.6%. At SF it is minus 14.3 to 10.2%. At FS it is minus 12.3 to 5%. We achieved 1 megahertz of frequency with plus or minus 14% of variation and 47% of duty cycle with 1.8 volt supply voltage with a variation of 10% in supply for a temperature range minus 40 degrees Celsius to 125 degrees Celsius. The current consumption was as low as 15.2 microamps. We are almost at the end of the presentation. These are the references that we referred while designing this oscillator. Thank you. Thank you, everyone. I would like.
Thank you. Any questions? I don't see chat. You guys want to ask one or two questions directly from audience?
So no questions.
Hello. Pooja, one question my side is, what is the maximum limitation of this ring oscillator frequency? For example, you want to increase more and more. What could be the limitation?
So limitations as in maybe we will consume more
we need more number of stages, but our specs was 1 megahertz, so we achieved these many.
I see. Okay. Thank you. Yeah, the next one is actually regarding the device. Let's see. This is the perspective of two-dimensional material-based, field effect transistor for analog RF applications. It's going to be presented by Arjun Kumar and Akhilesh Rawat and Brajesh Rawat are from IIT Ropur. Please start the video, please, and then bring the questions also. I'm reminding one more time chat window, so that will be I can ask the questions. Admin, please proceed the fourth presentation.
Hello everyone, myself Arjun Kumar. I am pursuing BTech in Electrical Engineering from Indian Institute of Technology, Ropur. Today I am going to talk about prospects of two-dimensional material-based field effect transistors for analog RF applications. I partitioned my today's talk into 5 parts. First, I will discuss the introduction and motivation of the work, and then I will talk about the approach which we adapted for the device simulation, and then I will talk about the device specifications, and then I will discuss the results and its comparison with silicon PET, and in the last I will give conclusions. Let us begin with a brief introduction of 2D materials. 2D materials have been becoming the most promising materials for the future high-frequency applications. Due to its atomically thin thicknesses, it has less source channel effects and high electrostatic gate controls, and due to its high carrier mobility, which results in higher on current and high ion-I-off ratio, and due to its surface free of dangling bond, it has less interface states, and it has also high effective mass, which results in low source to channel tunneling and hence low leakage current. And we have shown some of the 2D materials such as graphene, black phosphorus, MOS2, WS2, WSE2, and this table summarizes their band gap, effective mass, and mobility. We have taken the MOS2 and black phosphorus in our simulations because it has high effective mass, which results in a low source to channel tunneling current and hence leakage current, and it has a high mobility, which results in higher on current that could lead to a better RF performance. With the advancement of fabrication technology of large area synthesis of materials like BP and MOS2, the 2D material-based FETs become essential to understand their performance for digital and analog applications. Further, the recent research in 2D and FAT have demonstrated the excellent switching performance for ultra-scale devices with higher on-current and on-off current ratio of the order of 5. And here we can see in figure 1a, it shows the input characteristics of MOS2 at VD 0.05 and 1 volt, and it shows it has almost the ion-I-off ratio of order 5. And in figure 1b, it shows the input characteristics of BP at VDS minus 1 volt, and it also have ion-I-off ratio of almost of order 5. But the RF analog performance investigation are still in the early stage of the development. The intrinsic cutoff frequency and maximum oscillation frequency have recently reported in the gigahertz range for BP and MOS2 FET. As you can see in figure 1c, the MOS2 is small signal current gain as a function of frequency, and it shows the cutoff frequency is almost in the range of the gigahertz. And in figure 1d, it shows the power gain of BP as a function of frequency. Here the cutoff frequency and maximum oscillation frequency is in the range of the gigahertz. So it is essential to understand the linearity performance for the future high frequency application of these materials. Let us discuss about the approach we have adopted for the simulation of the devices. We have adopted the NEGA formalism to incorporate the quantum effect and the essential physics of the 2D material, in which we have developed the 1D tight binding Hamiltonian, which depicts the whole devices, in which we have taken the the effect of source and drain by accounting the self-energy matrices in the 1D tight bending Hamiltonian. And we have solved the 2D Poisson equation self-consistently with NEGF for a particular convergence. When convergence is achieved, we have calculated the current using the Landauer current equations, and we have taken the scattering effect separately by using dissipative factor. We have validated our models with first principle tools based on the DFT simulations. However, our simulation models have matched experiments qualitatively due to big difference between the considered device geometry and the limitations such as channel length, interface state, and the contact resistances of the current fabricated 2D material-based field effect transistors. And for SI FET, we have used the nanomos model based on the same approach, and we have taken the transport along the low effective mass directions. And here figure 2a shows the schematic of device geometry with 2D material as channel source and drain. And this table summarizes the parameters and the effects we have taken into the consideration during the simulations. We have taken the gate length of 14 nanometer because it is going to be the expected promising options for the future high frequency applications. And we have taken the source length and drain length of 20 nanometer of N-type dope with a concentration of 5 into 10 power 17 per meter squares. We have taken the oxide L203 of thickness 3 nanometer, and for uniform performance comparisons, we have fixed the I of current at 10 nanoampere per micrometer. For achieving this, we have tuned the metal work functions, and we have taken the minus 0.27 electron volt for BP and MOS2 and minus 0.6 electron volt for silicons. Let's discuss about the results. And figure 3 shows the device characteristics, and 3A shows the transfer characteristics at VDS 0.4 volt for silicon MOS2 and BP, and 3B shows the output characteristics at VGS 0.6 volt for SI, BP, and MOS2. The transfer and output characteristics, we can see it has an off current of almost 10 nanoampere per micrometer, and the BP and MOS2 FET has higher on current than that of the SI FET at high VGS because it has a better gate control due to its thin atomically thickness. And at lower voltages, at low VGS, the SI FET exhibit marginally higher on current than that of the 2D FET. The subthreshold swing for BP, MOS2, and SI is found to be around 64, 68, and 99.3 millivolt per decade. The degradation of the subthreshold swing in silicon is due to we have taken the transport along low effective mass directions because it has high source to channel tunneling current. And figure 4 shows the RF performance matrix at VDS 0.4 volt. And 4A, figure 4A shows the variation of GM with respect to the gate voltage, and here we can see the 2D material, specifically BP, has higher GM than that of the SI and MOS2. And figure 4B shows the gate capacitance variation as a function of gate voltages, and here we can see the MOS2 FET has higher gate voltages than the BP and silicon because gate voltages is the combination of the oxide capacitances and quantum capacitance, and as the MOS2 has higher effective mass, it has a high density of state and hence high quantum capacitances, which results in high gate capacitances. And figure 4C shows the cutoff frequency versus drain current, and in which we can see it has almost almost nearly the same for these three materials, and it is in the range of the terahertz. And figure 4D, it shows the maximum oscillation frequency as a function of the drain current, and we can see here SI FET has marginally higher maximum oscillation frequency at the same current level than that of the 2D material FET. Figure 5 shows the higher order transconductance at VDS 0.4 volt, and figure 5a shows the variation of second order transconductance GM2 as a function of the VGS, and figure 5b shows the third order transconductance GM3 as a function of the gate voltage. And since the linearity performance of MOSFET is mainly determined by the GM2 and GM3, so it is essential to determine the amplitude of GM2 and GM3 for linearity performance investigations. And the SI FET has a smaller amplitude of GM2 and GM3 component at high VGS, while that of the 2D FET has a smaller amplitude of GM2 and GM3 at low VGS. And figure 6 shows the harmonic distortions at VDS 0.4 volt, and figure 6 shows the second order distortions HD2 as a function of gate voltage, and figure 6b shows the third order distortions HD3 as a function of gate voltage. And HD2 and HD3 is mainly depends upon the GM2 and GM3 respectively, and it should be low for better linearity performance and less distortions. And SI FET has lower amplitude of HD2 and HD3 than that of the BP FET and MOS2 FET, so it would suffer from low distortions and have better linearity performance. Figure 7 shows the linearity matrix at VDS 0.4 volt. It shows the variation of IIP3, VIP2, VIP3 and IMD3 as a function of the gate voltage. These are all the valuable metrics for determining the distortion characteristics of a device. And further, the high value of IIP3, high value of VIP2 and high value of VIP3 and lower value of IMD3 represent the improved linearity performance matrix and lower distortions operations. And figure 7a shows that the third order intercept point IIP3 of the SI MOSFET is higher than that of the BP and MOS2 FET because it has a lower GM3 values. And we can also see the IIP3 peaks is observed at the zero crossover point of the GM3, so it shows that the device biases at the zero crossover point of the GM3 shows the improved linearity performance. The second order voltage intercept point and third order voltage intercept point are also higher for SI MOSFET than that of the 2D material FET. And the figure 7D shows that SI MOSFET has a marginally higher value of IMD3 than that of the 2D material MOS2 and BP FET. We have systematically investigated the RF and linearity performance of BP FET, MOS2 FET, and silicon FET using quantum mechanical simulation for a gate length of 40 nanometer, and we have found that for a given power, the monolayer BP FET shows higher on current and enhanced cutoff frequency, but it shows degraded linearity performance over the SI FET and MOS2 FET. The SI FET shows better RF linearity performance because it has superior values of BIP2, BIP3, HD2, HD3 and IIP3 in comparison to BP and MOS2 FET. And it is expected for the 2D material FET to have a better linearity performance because it has a higher on current and enhanced cutoff frequency, but it has a marginally lower value of VIP2, VIP3, HD2, HD3 and IIP3. So further studies on 2D FET should focus on understanding the role of material and device design parameter to improve the linearity performance for future high frequency applications. Thank you.
Thank you, Arjun. Yeah. Any question? Actually, I'm getting the questions late. There are 1-2 questions from the previous presentation, but it may not be fair to go those two now. Any questions on this presentation for Arjun?
Sir, I'm not seeing any questions in the chat box.
No. Mr. Punara, what is happening is our EQ tribe, which is the backend server, that is not 100% functional. So what is happening is that we are getting a delayed Q&A response from our participants. So that's the reason there is a delay actually, but nonetheless, you can go ahead and ask questions and we can move ahead.
Yes, you are saying that we can ask the questions on the previous presentation right now?
Maybe you can do that, yes.
I see. Okay, let's ask this current presentation just now. Arjun finished, and then we will back to the previous presentation.
Great,
questions.
great. Yes, please,
Yeah.
please.
Thank you. So, any questions on this presentation from the audience?
I do have a question. This MOS to how far does the author think that this will be coming into the mainstream technology domain in next 5 years?
Yes. Yeah, it will require so much time because right now the current MOSFET that is fabricated is around the 65 nanometer. There are some studies are there on 1 nanometer, but the contact resistance and this play a huge role in this getting a best performance. So maybe it require more effort. The CVD is one approach that can use to produce high quality MOS2. But still, the device level performance optimization, contact resistance, and interface charge, these are our optimization is required. So maybe it may take around 5 to 6 years down the line. But the other important way they are exploring, that is the hybrid integration with silicon technology. So some part could be there with the silicon technology, and integration with silicon will be a one option that can be explored in coming 5 or 6 years can be possible this way.
Okay.
Okay, thank you.
Thank you.
And Vikas this side, sorry, can I ask one question?
Sure.
Yeah. Actually, as the technology is shrinking, so there are two main parameters in the MOS which are impacting the performance. One is the velocity saturation, and another one is the DIBL, drain-induced barrier effect. So, do you think these effects will be present in this MOS also? And if not, how they are being taken care?
Yes, thank you, Vikas, for a very good question. So actually, in MOS2, is all DIBL and all short channel effects will be there. So, but the value of DIBL it is found in the literature. Our work is not more focused on the short channel, but in our previous paper we have studied those parameters. So DIBL is smaller compared to MOS2, and the important thing, whatever this silicon MOSFET is very difficult to scale down to 1 nanometer, but along with the CNT and MOS2, it is possible to get a on by off ratio of order 10 to the power 5 even at 1 nanometer channel. But that is not possible with the silicon MOSFET. So all parameter will be there, but the compared to because of the thin atomic layer, the capacitance, springing capacitance will be smaller and other thing. The better gate control is there. So the short channel parameter will improve in case of the 2D material compared to silicon MOSFET. But we can see all the parameter, all the short channel effects will be there in the 2D material FET also. Thank you.
Okay, thank you.
Okay. Yeah. Thanks, Arjun. I think no more questions.
Thank you. Thank you.
Admin, can you please unmute the Pooja Shanbag for the ring presenter who presented the ring oscillator with improved design? The two questions are there from the audience. We'd like to go through those two. Yeah. Is it unmute? Right? We can ask the question. Hello.
Hello. Yes. Is there some question, Mr. Punara?
Yeah, we need to unmute that Pooja Shanbag so that I can ask the questions on the previous presentation on the ring oscillator with improved design.
Pooja Shanbag.
Yep.
She can unmute herself.
Okay. Sounds good. So the first question on this is from Vivek Tyagi is asking, does any startup is used in the current generator? The voltage that you guys are using in that ring oscillator supply. Okay.
Sorry, Mr. Punara, I don't think Pooja is here.
Oh, I see.
So Pooja Shanbag, is her presentation over?
Yeah, it's over. This is the two questions on the, yeah.
She seems to have left the meeting.
Yep.
Okay, fine.
Okay, then let's. There is one question, Arjun Kumar. If you bear one more question, do you have any prototype 2D structure for MOS2 and BP in applications today? It is from Sarkar.
Yes, actually, there is a no prototype is there. There is no industrial level application. There is not much material is there. But photoelectronics, they are working with this one for this way. But right now, there is not any industrial level prototype is there. But we have developed one FAT on. We are working on this one, especially for biomedical application. We are developing FAT. But not the commercial level integrated. FAT is not there for integrated circuit. Either digital or IC. There is a no commercial product.
Okay. Thank you.
Thank you. Thank you.
Yeah, the last presentation today. It's a novel low power electronically tunable higher order quadrature oscillator using CBDA. It's from Shekhar Suman Bhora, Ankur Singh, and Morina Ghosh from IIT Guwahati, Assam. Admin, please start the fifth presentation.
Hello everyone. Today I am going to give my presentation on a novel low-power electronically tunable higher-order quadrature oscillator configuration using current differencing buffered amplifier. My name is Shekhar Suman Bhora and I am from IIT Guwahati. So these are the main outlines of my presentation. Introduction, current mode circuits, the current differencing buffered amplifier, the proposed quadrature oscillator configuration, simulated and experimental results, application of the proposed mode, a comparative study of the proposed work with earlier reported works, conclusion, and finally the references. Introduction. We know that voltage mode and the current modes are the two regulating conditions that controls the output of a power supply. So in most of the today's applications, call for a supply to be used as a voltage mode. In voltage mode, the power supply provides the constant output voltage while providing the required current to the load. But in current mode circuits, the power supply provides the constant current to the variety of load voltage conditions. So these two regulating mode works to provide the constant control of the supply. So in current mode circuits, the information is represented by the branch currents rather than the nodal voltages as that of the voltage mode circuit. So here, the current rather than the voltage is primary. So we can find the applications of the current mode circuits in the field of analog signal processing, telecommunication systems, instrumentation, etc. So this work presents a novel topology of current differencing buffered amplifier based higher order quadrature oscillator configuration. So the proposed design consumes 0.917 milliwatt power and it is proficient in performing with a minimum supply voltage of 600 millivolt. The simulations were performed using TSMC 180 nanometer CMOS process parameters, and the proposed design is also experimentally tested using commercially accessible IC 8844EN. Additionally, the layout of the layout is designed using the analog design environment tool of Cadence Virtuoso to confirm the workability of the proposed configuration. The current mode circuits. So the first question comes to our mind that why the shifting from voltage mode to current mode was important. So since the introduction of the integrated circuits, so the voltage mode operational amplifiers such as LM741, LM341 have been used as a basic building block for a variety of applications. But the performance requirements have been changed over the years, and it was observed that voltage mode operational amplifier makes the circuit more complex whenever the low voltage, low power supply and the wide bandwidth is required at the same time. Also, the slew rate is less compared to current mode circuits. That is why it is unsatisfactory at the higher frequencies. So the slew rate of the current mode circuits is higher. That means it can provide the satisfactory results up to the 6 MHz of frequency, whereas in operational amplifier, voltage mode operational amplifier can provide the satisfactory results up to 1 MHz of frequency. So the basic unit of the current mode circuits are called the current converters. The first current converter was introduced by Sir Brian Smith in 1968. There are different types and different generations of the current converters, which are like first generation current converter, second generation current converter, third generation current converter, current control current converter, multi-output current converter, etc. So other than these current converters, there are some other current mode based circuits, which are like operational trans resistance amplifier, the current differencing buffered amplifier, operational trans conductance amplifier, differential difference current converter, differential voltage current converter, etc. So in the proposed work, the CDBA, the current differencing buffered amplifier, is used as an active element. So the current mirror concept, so it is basically used for the implementation of the internal structure of the current differentiating buffer amplifier. So the current mirror concept says that the output current should be the mirror image of the input current. So in the as shown in figure 1, where I naught is the output current and I reference is the input current. So now where we can see that the terminal D, the drain and the gate terminal is shorted. That means the VD is equal to VG. So that we can write VDS, that means the drain to source voltage is equivalent to the gate to source voltage. From where we can write VDS greater than equal to VGS minus VT. So VT is nothing but the VGS, that means the minimum voltage at which the transistors starts operating. That means it is a saturation region. So after solving these equations, we can get I naught is equivalent to the I reference current other than these aspect ratios. So the current differential buffer amplifier. So CDB consists of the unity gain current differential and the voltage amplifier. It consists of 4 terminals. P and N are the input terminals and W and Z are the voltage and the current output terminals. So the current voltage relationship can be represented in this matrix form. From here we can see that Vp is equal to Vn is equal to 0. That means the input terminals are internally grounded, so thereby eliminating the parasitic capacitances. Also, the current flowing current at the Z terminal is equivalent to the difference between the input currents. That means the Ip minus In. Also, the Vw is equivalent to Vz. That means the voltage at the terminal W is equivalent to the voltage at the terminal Z. So figure 3 represents the implementation of the CDBA using MOSFETs, where the P MOSFETs are connected to VDD and N MOSFETs are connected to VSS. Where this is the P terminal, this is the N terminal, this is the W, and this is the Z terminal. Where IB1, IB2, IB3 and IB4 are the bias currents and VB1 is the bias voltage. Here the current mirror concept is utilized. That means the current flowing through this terminal is equivalent to the current flow through these terminals, and this process continues. So here VDD and VSS is considered as 600 millivolt for the proposed configuration. CDBA can also be realized by using commercially accessible IC 8844 by utilizing for breadboard verification. Here two 8844 ICs have been used to get the characteristics of the current differentiating buffer amplifier. So this is the proposed quadrature oscillator configuration. So quadrature oscillator circuit produces the sinusoidal outputs possessing a phase duration of the 90 degree, where the sinusoidal waveforms are taken from these two terminals V01 and V02. Here two CDBAs as an active element have been used with some passive components. So the characteristics equation of the proposed quadrature oscillator in terms of passive elements can be obtained from RC decomposition technique, which is this is the transfer function. Figure 3 represents the transfer function. Also the frequency and the condition of oscillation are expressed in equation 4 and equation 5. By the proportionation of the CA2 and RA2, we can electronically control the frequency of oscillation. Also, by the proportionation of the C1 and R1, we can control the condition of oscillations of the proposed higher order quadrature oscillator configuration. So sensitivity analysis. So sensitivity is basically analyzed to check how the one function changes as a function of the another thing that is changing. So here the sensitivity of the passive components such as resistors and capacitors with respect to the frequency of oscillations have been calculated. It is found that the sensitivity is within unity. That means it can provide the satisfactory results. So figure 7 shows the simulated results, the transient and the steady-state response of the proposed higher quadrature oscillator configuration. So this is the steady-state response at the terminal V01 and V02, which provides a phase shift of 90 degree. And the frequency spectrum, the proposed structure is designed for 68.056 kilohertz, and the frequency spectrum is obtained around 69 kilohertz of frequency. And the figure 8 shows the quadrature relationship between the generated waveforms. So this is called the Lysis Pattern. So this is basically calculated to check the phase difference between the two sinusoidal signals having the same frequency. As these two terminals are the same frequency, so this provides the Lysis Pattern. This is the V01 terminal. This is the V02 terminal. So next one is the simulated results for percentage of the total harmonic distortion. As the circuit is designed for the 68 kilohertz of frequency, so the DHD is around 3.5%. So we can say that it can provide the satisfactory results up to 100 kilohertz of frequency. frequency where THD is below 10%. So figure 10 shows the temperature variations from 20 degrees Celsius to 100 degrees Celsius. So there are no sharp variations perceived if the temperature changes is observed. So figure 11 shows the steady state response of each one at different process corners such as normal, slow, and fast, where you can observe that there is a slight variation of the amplitude, but there are no sharp variations are observed. So these are the experimental results. So for the breadboard verification, the proposed circuit is designed using commercially accessible IC 8844AN. So here 4 8844 ICs have been utilized. So this is the terminal V01, this is the V02. So figure 13 shows the experimental steady state response of V01 and V02, and figure 14 shows the experimental frequency spectrum, which provides the frequency of oscillation is around 70 kilohertz of frequency. There is a variation of the 3% with respect to the theoretical frequency response due to the 10% tolerances of the passive components. The figure 15 shows the layout of the proposed design. The layout have been designed by using analog design environment tool of Cadence Virtuoso. So the layout consumes an effective area of around 12,400 micrometers square, and the figure 16 shows the post layout steady state response that verifies the theoretical and simulated hypothesis with respect to the layout. So the application of the proposed hybrid quadrature oscillator configuration. So an application outlook of the stated configuration is studied for the transmission and the reception of the quadrature amplitude modulation signals. So figure 17 shows the quadrature amplitude modulation for modulator and a demodulator with two independent message signals such as XIT and XQ of T, which are modulated by two carrier waves with same frequency but having phase shift of 90 degree. So here the proposed quadrature oscillator have been utilized, and YIT and YQT are the detected signals at the receiver. So figure 18 shows the input signals XIT, and B shows the XQ of T. So this is the output of the transmitter. So output, the receiver in figure 20 shows that the output messages are separated by YIT and YQ of T. So it can be observed that the output is the same as the input. That means it provides the verification of the proposed hybrid quadrature oscillator configuration. So the comparative summary of the proposed work with the earlier reported work is also studied, from where we can observe that the supply voltage and the power consumption is less compared to the earlier reported work. Also, in earlier reported works in reference 12 and reference 14, more than 2 active building blocks have been realized. So in the proposed work, only 2 CDVS are used as an active element. So the transistor count is also less compared to the earlier reported work, other than reference 12, where 24 transistors are used, but the number of active building block is more compared to the proposed work. Also, the frequency of oscillation is less compared to the proposed work. So the conclusion. So in this work, a novel low voltage, low power CMOS CDVA based 4th-order quadrature oscillator configuration is presented. So there are we can summarize our contribution as here only 2 active building blocks are used, such as CDVA. Simulated and experimental results are performed using both CMOS and BJT based IC 8844AN for the breadboard verifications respectively. So the number of MOS transistors are also very less. Low supply voltage and low power consumption. Also, the electronic control feature is also available. The sensitivity and the percentage of the total harmonic distortion is also significantly less. So these are the references. Thank you.
Thank you, Shikhar. So, any questions for other?
There's a question from audience side. You can just continue, please.
Sorry, it's cut. I mean, some cut happened in the sentence.
There is no question from audience side. You can please continue.
Okay. Okay, I have only one last question on this. Is the metrics when you compare the sensitivity? I mean, the sensitivity or the quality of that new proposal is also verified. I see the other power things are. I see that. See how much percentage we had better this new approach?
Yes, sir. So the quality factor is also checked, which is within unity compared to in previously earlier reported papers, which was also we have found within one. So in our proposed work is considered the higher order oscillators. The quality factor is within unity.
Okay. Thank you.
Thank you, sir.
So if there is no more questions, and thank you all for your presentations, and the audience also for successfully completing this first technical session. I think we can close. Admin, you haven't to add any other statements in the closing session, or we can close it right away.
Thank you, Dr. Punarao. So we'll be closing this session now, and we'll be resuming next keynote session from 1:30 as per the schedule. Thank you all.
Thank you all.